conserve 20 to 26 amino acids. In other words, it will vary from one protein to another. So it is the hydrophobicity that is recognized. It will bind and stop translation, haul everything over and line it up, at which point it will leave, SRP will leave, and translation will resume. And we have these different pictures to look at here. And then you saw, I mentioned to you that sometimes you go through the membrane one time, sometimes you can go through multiple times. All of those directions are encoded for us within that string of amino acids. Say stop, start, stop, start. Let's say you get a multipass protein. Okay. So sometimes all the way through as this is transmembrane protein, sometimes entirely is independent. But the one thing that each one of those that we just saw had in common was this signal peptide at the very end terminus, the part that was first made. Okay, moving on, we're going to add sugars to proteins. Now remember, we are in the ER, and this is co-translational processing. In other words, as the protein's being translated, it's being inserted into the ER. Now, what we're going to do is take a regular protein and we're going to add sugars to it, and of course we all know that that's going to make it a glycoprotein. There are two ways to glycosylate a protein. One way is called N, should really be N-linked glycosylation. Y'all want to take good notes because you have a lot of information here. The other way will be O-linked glycosylation. We're going to be adding sugars onto the protein. In the N-link, this happens in the ER, endoplasmic reticulum. For the O-link, it happens in the Golgi. The Golgi will be subsequent to the ER. They leave the ER and go to the Golgi. So that's in the Golgi. In this case, the N stands for asparagine. It's the one-letter codon for asparagine. The O, unfortunately, stands for hydroxyl. There is no amino acid with an O. So this is for an hydroxyl group. So you're going to be adding sugars on to something that has an OH hanging up there. And you know it will be one of 3 amino acids, which would be 3. Good. All right. That's music to my ears. Except it was a very scant chorus over here. I know you're trying to write and listen and at the same time. So anyway, that's what we're looking at. So here we go. We are moving into the ER. We're being translated as a protein that started out life with a signal peptide. And what's going to happen is this. If you have the sequence, if you have this particular sequence, very, 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 very important, of asparagine, followed by any amino acid at all except proline. Can't have proline there. No pro. Pro's not allowed. Followed by serine or threonine. Then you will be able to have sugars added to your asparagine. Very, very controlled addition of sugars. So asparagine followed by some amino acid other than proline, followed by either serine or threonine. Those are the requirements. In this picture, they have shown you that, but it's a little confusing. So look right here. Here's your asparagine. And they're saying that's followed by anything they don't say except proline, but you might want to make a note there. Proline would do what to that protein? Kink it, yeah. So that's not going to work. And then the serine or the threonine. Now what's going to happen is that asparagine is going to receive 14 sugars. These 14 sugars are pre-assembled and ready to go. So if, as you're being translated as a protein, you're entering the ER, and you have that signal sequence there, you will end up with 14 sugars added to your asparagine. Subsequent to that, we'll play around with those sugars. We might take some off, we might change a few around, but everybody starts out with the same 14. The 3 sugars that are added are here. I'm not requiring you to know that. I do require you to know 14 sugars are added. So where did these come from? The 14 sugars were already, as I said, pre-assembled. They were made, and they were held attached to the endoplasmic reticulum membrane by this particular phospholipid, or this lipid. It's not really a phospholipid. Dolichoyl bisphosphate. That's DOLICHOL. I know sometimes it doesn't print out well on your handouts, but dolichoyl bisphosphate is the lipid that has pre-assembled this group of 14. 14 sugars, many sugars, oligosaccharide. So this oligosaccharide is lipid linked because dolichoyl is a lipid. Okay, so what happens is this. Here's the asparagine, and we're going to assume the correct 2 amino acids are coming along behind there that we spoke of on the previous slide. So what's going to happen is an enzyme is going to come along here and cut those 14 sugars off of dolichoyl bisphosphate. And that same enzyme is going to attach this now to the asparagine. So bingo, in one step here, you have N-linked glycosylation occurring, and you are inside the ER. You're in the lumen of the ER when this happens.
And which enzyme is this?
Thank you. That enzyme. Oligosaccharyl transferase. Thank you, I left that out. That's very important. Probably you'll be asked that. It's not a hard enzyme to remember. You know, the ACE tells you enzyme. It's an enzyme that's going to transfer something. Well, what is it going to transfer? Many saccharides, many sugars. So oligosaccharyl transferase, know that enzyme. It's the one that comes in, cuts them off of dolichoyl bisphosphate, and attaches them to the appropriate asparagine. Very, very, very important. So that's the first of the 2 ways to add sugar to your protein. Okay. Now, in the previous slide, you had the sugars added to the protein, and now you're getting all ready to leave the endoplasmic reticulum. If you remember your diagram that I told you to keep referring to throughout the rest of the course, the only place you can go when you leave the ER is Golgi. One person. Golgi. I'm going to say it again. The only place you can go when you leave the ER is the good. Catechism class here. Okay, that's very, very important to remember. Now, before you're allowed to leave the Golgi, you have to be checked. You have to have another protein look at you and say, okay, you had those sugars added onto you, right? If you were N-length glycosylated in the ER, you don't get to leave until we put you through this little check. Here's the check. So this time the lumen's on the top, not the bottom. So we're still inside the ER. And here is our protein, this green thing, and the blue stuff on there would represent the N-length glycosylated sugars. So what happens is this. You have chaperones. Chaperones are nothing more than helpers, and they do use ATP. Some instructors call them chaperones. That would be O-N-I with proteins that help other proteins fold correctly or go to the right place. But anytime a chaperone helps you, it burns up ATP. Nothing's free. Okay, so here's what happens. Calnexin is one of these chaperones. It is a membrane-bound chaperone in the ER membrane. And what it will do is take you as an N-length glycosylated protein and check you out, okay? So what's going to happen is this. You're going to go through, this is a multi-circle type thing, so we're just going to start here at the bottom. But you will go through, I guess I better stop. Kind of like there's no good place to start the circle. Okay, let's start the circle here. So here's our N-length oligosaccharide, a protein with the sugars. Let's go up this way. Well, boom, somebody has checked us and we're not folded correctly, or something else is wrong. In this case, it says incompletely folded. In that case, you're not going to be allowed to leave. So what's going to happen is this. You're going to go in there and have a glucose removed, the very end glucose from your string of 14 sugars, and you're going to get a chance to kind of get your act together and come back and get checked a second time. I guess starting here is the first time. If you are still not folded correctly in this case, you will be sent around again. You go through the same process where you have a glucose removed and another one put on. It's kind of a change the tires on your car when they're all worn out. And if that makes your car drivable, fine. But if it doesn't, then you just got to keep fixing things till you get it right. So what usually is given as the figure is 3 times. You get 3 chances to go around here and get your act together. If you do not fold correctly or whatever, you still flunk the test, you will actually be sent out from the ER and you're going to be destroyed. If, however, you're okay, like 3 times you're all okay, then you're allowed to go to the Golgi. So what happens if you get kicked out of the ER? When you get kicked out of the ER, remember, now we're back down on the bottom. There's the ER limit. I wish you would keep the orientation the same on adjacent slides, but here's the ER limit. Here's the chaperone that's been looking at you saying, well, you just still couldn't get it together for 3 times, so you're leaving. You actually end up having that chaperone take you up to the same translocator pore, that protein through which you entered, and it will boot you out into the cytoplasm. So this is the cytosol up here. In the cytosol, you are going to be ubiquitinated. Remember that story where you add on the ubiquitin? So you have this one ubiquitin flag that's going to say, take me to the proteasome, and chew me up, except we know that if you add a second one onto the first flag, like this big long flag, you are going to be more recognizable, I guess you could say.
So you're, I'm sorry, is there some sort of sequence that the chaperone is just going to recognize, or is it something else?
It's really a shape type thing.
It's a shape?
Yeah, it's a shape type thing. It's a very specific shape that final confirmation has to have. And I'm making it sound a little more magical than it really is. I'm just going to leave it at that, if that's okay with you.
So chaperones have been more quality about it.
Yeah. They're not good. They actually, I'm looking at the glucose, it's an overall thing, because, they can't go in there and read the amino acid sequence or anything, so everything is about charge, density, shape, and so forth. Okay, so there you are, eaten up in the proteasome, and then your individual amino acids are spit out, and guess what? You can turn right around and use those in translation to make a new protein, and maybe have better luck in your second life than your first.
So is that an asparagine glycanase that's going to take the sugar back off before it goes to the proteasome?
Yeah,
Is that what that's supposed to be?
yeah, I was trying to avoid that. It's a very good question. That didn't come